Hello, everyone. It is my great pleasure to be speaking with you here. Unfortunately, I cannot be with you today in Paris, but I hope to meet you in person very soon. So today, I'm going to speak about my joint work with my student Zhixu on projections with log divergences. So let's begin with a review of the concept of log divergence, which is the main object of study in this work. The log divergence basically is a generalization of the Bregman divergence. So let's recall that the Bregman divergence is defined for a convex function. Here, we look at a parameter alpha, which is positive and fixed, and a domain, which is a convex set. A function phi on this domain is said to be alpha exponentially concave if e to the alpha times phi is a concave function. So this big phi is a concave function, and its log divided by alpha is alpha exponentially concave. We can express the concavity or the alpha exponential concavity of phi by means of this second order condition, which is that the Hessian of phi corrected by this term is positive definite. Because of the exponential concavity of this function, suppose that I have 2 points, theta prime and theta here. And usually for the Bregman divergence, we use the straight line, which is the tangent hyperplane. But because of the alpha exponential concavity, we can use a curved first order correction. And the error coming from this correction gives us the so-called L alpha divergence, which was first introduced in my joint work with Schmidt in 2016 and also extended in my later work in 2018 and 19. So it is defined as follows. So I first look at the first order linear approximation, and then I have a log correction with the log here, and then I look at the difference of the functions. So it can be shown that this quantity is always positive, and it gives you this error term here. And as alpha tends to 0, suppose that we let alpha tends to 0 here, then we obtain just the linear term, and we recover the Bregman divergence. So this is the concept of the logarithmic divergence, where alpha, which is positive, is fixed. So you can think of this as a parametric extension of the Bregman divergence tailored for exponentially concave functions. So this log divergence is very interesting from the information geometric point of view. First of all, suppose that we look at this log divergence as a divergence on this convex set regarded as a manifold. Then in information geometry, we know that it induces a so-called delistic geometry consisting of a Riemannian metric G as well as a pair of affine connections, nabla and nabla star. So remarkably, I showed that this delistic geometry is actually duly projectively flat and its sectional curvature is constant. Moreover, the L alpha divergence is a so-called canonical divergence of such a geometry. So this means that if I start with a statistical manifold which satisfies these properties, then locally I can define intrinsically a divergence which is given by an L alpha divergence. And this L alpha divergence also plays a role in probabilistic modeling. So consider the heuristic, which is that I consider a probability density such that is which is proportional to e to the minus of the L alpha divergence. So you can think of this as a generalization of exponential family, and in particular the normal distribution where you have minus of the square of the squared distance here. So if you plug in the L alpha divergence, it leads to a generalized exponential family or a deformed exponential family that I call the F alpha family, and it looks like this. So if you let alpha tends to 0, then we recover the exponential family, and this normalization function here can be shown to be alpha exponentially concave, and is L alpha divergence can be shown to be the Rayleigh divergence. So our geometry here is a very natural, and it's compatible with this generalized exponential family, which is closely related to the Q exponential family. So here I can think of this theta as the primal variable, and the dual variable, which I call eta, is defined by this generalized gradient. So I have the alpha gradient, which is the ordinary gradient divided by this scalar here. And if we define this eta in this way, and also if we define the so-called alpha conjugate of this phi by this conjugation, which is a generalized convex duality, then we have this identity. And we also have that the L alpha divergence is self-dual. So the L alpha divergence of psi is the same as the alpha divergence of phi, but with the arguments swapped. So let's look into the geometry of this L alpha divergence in a little bit more detail. And we also showed before that the L alpha divergence satisfies what we call generalized Pythagorean theorem. So let's consider the so-called Pythagorean relation, where I look at 3 points, P, Q, R, and I ask whether the divergence from P to Q plus the divergence from Q to R is equal to the divergence from P to R. So it is well known that the Bregman divergence satisfies Pythagorean's theorem, and here it is also true for the alpha divergence in exactly the same way. So in particular, this Pythagorean relation holds if and only if the so-called primal geodesic between Q and R, given by a straight line between Q and R, but run in non-constant speed, is orthogonal to the dual geodesic, which gives a straight line using the dual coordinate system. So we have a situation which is very similar to the Bregman divergence, which is dually flat, but here we have a curvature which is equal to minus alpha. So this Pythagorean theorem allows us to look at primal and dual projections. So here let's look at just the dual projection, which is given as follows. So suppose that I have a submanifold E here, and I also have a P. And let's look at the point Q on E, which is closest to P when measured in terms of the L alpha divergence. And this point is called the dual projection. And the Pythagorean theorem can be used to look at the first order conditions. So namely, the dual geodesic from P to Q has to be orthogonal to E. So this is the first order conditions. And our first main results here is a dual foliation based on this primal and dual projections. So let's look at this picture and see what, and look at its geometry. So suppose that A here is a convex or affine space in the primal space, which is big theta, and consider the alpha gradient, which I denote by T. So I use T because this can be related to a transport map. And under this transport map, the A space, which is convex here, is mapped to a nonlinear submanifold, which I call E, in the dual space, which is the space of the domain of the dual coordinate system. But intrinsically, you can think of these two spaces as the same space. And what's more, this A is so-called primal autoparallel because it is convex in the coordinate theta, and the geometry is projectively flat. So what do we have here? Suppose that I look at a point Y, which is not necessarily on the set E, and let's look at the dual projection, which is eta. So by construction, the dual geodesic, which is the straight line in the dual coordinate space, is orthogonal to this E. Okay, so in other words, if you look at any point on this straight line, so which is here a straight line, but in general it is a k-dimensional manifold, like a d minus k-dimensional manifold. If this E has dimension k, then all points on this gray submanifold are projected to the same point eta, and let's call this d of eta. Okay. So this d eta is convex set in the Dirichlet coordinate system. And so it is a dually autoparallel. And by the Pythagorean theorem, it is orthogonal to E at this point eta. And for different points eta, the corresponding dual complements, which d eta, are disjoint. So this gives us a disjoint union of the space as the union of these complements d eta, where eta ranges over my original set E here, or equivalently the A here. So this result is what we call a dual foliation, because it gives us a disjoint union of the manifold, and also they are all orthogonal to the same base manifold A. And these results generalizes a result by Amari, which gives a dual foliation for the Dirichlet case, or equivalently the case of the Bregman divergence. So our second result in this work is to apply this theory to look at dimension reduction. So, and in particular, we look at the concept of principal component analysis. So as we all know, principal component analysis is an important method for dimension reduction. And the most common way of doing principal component analysis is to look at the Euclidean Pca, which amounts to doing an orthogonal projection. So here I have a picture for Euclidean Pca, where I have data in a 2D space. And if you look at its covariance matrix, the first principal component gives us the first eigenvector corresponding to the largest eigenvalue. So here, this is the Euclidean Pca, which assumes a Euclidean geometry, or equivalently a Gaussian probabilistic model that generates the data, so that the mean is constrained to lie on a linear subspace. We can also think of the Euclidean Pca in terms of optimal transport in unequal dimensions, although I'm not going into detail here. So in this work by Collins and collaborators in 2003, they extended the Euclidean Pca, which corresponds to the Gaussian model, to the exponential families. And they call this methodology the Exponential Family Pca. So in Exponential Family Pca, instead of minimizing a quadratic loss function, they minimized a Bregman loss function. And this is because the exponential family is closely related to the Bregman divergence. So the main idea of this work is to extend this idea to the Alpha divergence, where I have an implicit probabilistic model given by this F alpha family. So here is the formulation of the so-called L alpha Pca, which we introduced in this work. So before looking into the formula, it is better to look at the picture here. So let's suppose that in the space of data, I have some data points that I call yi. Okay, and I also fix an exponentially concave function psi on the dual space here. So what we do is that, similar to the dual projection, we look at a convex set in the primal space of parameters, which corresponds to a curved submanifold in the space of data. Then we project all these points to this E using the dual projections, so that the dual geodesic here is orthogonal to the E. And so for each projection, you look into the L alpha divergence between the point and also the projection point, and you add this up, and you will get this cost here. And the goal of this L alpha Pca is simply to vary the A over all convex subsets of this parameter space with a fixed dimension, and that is Pk, so as to minimize the total lost here. So this is the formulation of the L alpha Pca. So let's say this again. So I first fix A, a convex set, and then for each data point, I project this dually onto E, and then I want to minimize over the convex set. And here the L alpha divergence is part of the loss function. So as I just mentioned, this problem corresponds to an inference problem if the underlying L alpha divergence comes from an F alpha family. So you can think of this as an extension of the exponential family Pca to the F alpha family or the Q exponential family. So here's an example where the underlying probabilistic model is the so-called Dirichlet perturbation model. So here the state space is the unit simplex, and I have two outputs here. So the black points are the data points, and here the blue curve shows the optimal primal autoparallel submanifold, and the red points are the projection points. So on the left-hand side, we see that we have a case where the points are already fairly close to the submanifold, and on the right-hand side, we have a more noisy data set, but still we have we can perform the PC and get the projections. And you see it here, the gray straight lines, these are the dual geodesics, and they are all orthogonal to the blue curve here, and they form part of the dual foliation. So, so this is not the only generalization of Pca to the simplex, and in compositional data analysis, there are several other geometries based on the Atchison geometry, but here our L alpha Pca based on this Dirichlet perturbation produces a different geometry, and it will be interesting to compare the results. So currently we're working on several projects. In particular, we will look at how to do these optimizations efficiently, and we also have other ideas about statistical applications of log divergences as well as optimal transform. So that's it, and thank you very much for your attention.